Start. Good morning, everyone. It's great to see so many of you here bright and early. Are you ready to engage in new ideas and practical solutions? Yes, awesome. I am Balaji Kumar, Principal Software Engineer at Amazon. I have been with Amazon over 12 years, worked in various teams. Currently, I'm working in Amazon Finance Technology team.
And also, thank you from my side for coming. We are competing with a keynote. Everybody is aware of this, and we are even more grateful that you are here. Hello, my name is Dirk. I'm a Principal Solutions Architect. I'm on the team of AWS in Germany. In my day job, I work with software companies on their multidimensional transformation, and integration architecture is one of my hobby horses, which comes in quite handy, because today we're going to talk about integration architecture. And actually, we're going to drink from a firehouse too. So why are we doing this in the first place? Because integration architecture is relevant for everyone. No matter if you work on a monolithic application or you have already started carving out maybe one of the first components on your monolith, or if you have already a divide and conquer architecture at home. Integration architecture is relevant for everyone. There are always systems that need to be integrated with each other. And maybe they are under your control, like the hoodoos here in the orange circles, or they are outside of your control, like third-party systems or SaaS solutions, illustrated by the blue circle. And also, when you think about your integration architecture, it is often a journey, and you want to be prepared for that journey. Like, when you want to drive on a bumpy road, you want to prepare yourself with a vehicle with high clearance and four-wheel drive. And in the same way, you want to be prepared for your integration journey with a good understanding of concepts and patterns. And this brings us to two insights. The first one is I'm only doing public speaking at conferences because I want to show off with my nice holiday photos. And the second insight is that in cloud applications, in modern applications, or in applications in general, you can say integration cannot be an afterthought. It is an essential part of your architecture. And again, this does not only apply to a divide and conquer architectural style like microservices or self-contained systems. This also does apply to heritage applications because you always need to integrate with something. So, how difficult can it actually be to connect two boxes or two systems with each other? Let's have a look at the conceptuals and the fundamental technology that we can use for integration. Already here, there's quite some ambiguity that can hit you. For instance, if you look at messaging versus streaming, the ambiguity is constantly growing because of the convergence of the features that each of those concepts or the products that implement those concepts bring. But even if we concluded on the fundamental approach, there are a lot of follow-up questions and aspects that we need to consider. And each of these aspects have their individual trade-offs. Trade-offs, that's the key word here. And this is the decisive term that brings us to the next insight. Because no architecture decision that you take comes without trade-offs. I also like this, the beware of the faith healer principle. I know we all want something that just solves our problem with any adverse effect, but the ugly truth is there's always something that sucks. Whatever you decide for your architecture, for your technology approach, there's always something that sucks. And as said in the beginning, no matter what architectural style, your integration decisions come with trade-offs that you need to be aware of and that you need to manage. I also said in the beginning, aspects of distributed systems are relevant for all kinds of applications. And this is why we want to use this talk to look into integration patterns from the viewpoint of some distributed system fundamentals.
Integration has evolved from being an afterthought to becoming a critical architectural decision that we make day one. Today, we are going to discuss 4 fundamental concepts. These are very important when we connect the systems in the distributed environment. First, coupling and its dimensions. In a distributed system, coupling defines how much system A needs to know about system B to work together. It could be their data format or location. Understanding this connection helps us to make better architectural decisions. Then we are going to discuss control flow and flow control nuances like are we pulling, pushing between the systems, traffic shaping, and back pressure. Then message order and delivery semantics like exactly once delivery, at least once delivery, FIFO channels, competing consumer, deduplication. Finally, error handling. No system is going to be perfect. When we have a lot of moving parts that can create failure, we need to understand how to deal them effectively. So without further delay, let's jump into the first concept, coupling and its dimensions. Coupling is an important concept that helps us to build robust and flexible software. Imagine for a moment, you are building a complex Lego structure. Each brick in this structure represents component of your software. If you glue this brick, you get the stable structure. But if you want to replace the particular brick or rearrange part of the structure, it's going to become nightmare, right? This is similar to tight coupling in the software. On the other hand, if you connect the bricks instead of glued, you get the flexibility without sacrificing the stability. This is exactly we aim for in software architecture, the right balance of connection and independence between the components. Coupling is not a binary. It is not coupled or uncoupled. It is like a spectrum. The interdependency between the components varies from very low to very high. We often call it as loosely coupled and tightly coupled. As you can see in this slide, there are two systems, A and B, has a dependency which is depicted by this arrow. Remember, when there is a dependency, there has to be some level of coupling. If the two systems are totally uncoupled, then there is no dependency, there is no need for this arrow. Also, decoupling offers you flexibility. However, the flexibility comes with the cost. You cannot simply decouple every component in your system because decoupling introduces the complexity and lot of moving parts. You might be decoupled by programming language. Still, you might be coupled by their location. We are going to see various dimensions of coupling in next few slides. But as an architect, it's very important for you to decide what is the right level of coupling required for your system. The statement here is, a structure is stable if cohesion is high and coupling is low. Cohesion here refers to what degree the internal contents of the modules are related, whereas coupling defines to what degree the modules depends on each other. Today we are going to see various techniques that will help you to keep the coupling low to achieve better stability.
Right, and coupling is all about dependencies between systems. So let's have a look at that. For those dependencies, there are lots of dimensions actually. But we want to focus on a subset of these dimensions that we think are most relevant in day-to-day architectural discussions, which are those four here: location, format, temporal, and domain. So let's have a look at some integration patterns and see how they touch on some of those dimensions. And let's start with the consideration of synchrony versus asynchrony. As we have learned also from Werner Vogel's a few years ago in his keynote, the world is asynchronous, and that's right. So we need to deal with asynchrony. All right, and asynchrony focuses on the temporal dependency between systems. For illustration, we can get back to our very simple two boxes diagram. And when we look at communication patterns, one-way communication seems to be the simplest one. A sender transmits a message to a receiver, and that's all. However, as users of web browsers or as software developers working on synchronous request response model or function calls, we are more used to the synchronous request response pattern. And we see it here implemented with APIs. And this is actually quite common for APIs. We can make it concrete by using HTTP connections for the communication. The decisive aspect here is that the responder is working on the request and the requester actively waits during the entire time. So let's have a look how that can look like in a system of systems and maybe a landscape of microservices. And here's an example of a dependency graph. I stole it from Adrian Cockcroft's GitHub page, and it illustrates quite well what you often see in a divide and conquer architecture. There's a request coming in from the outside, and then it will take a path through this dependency graph. And when we implement this with synchronous request response, we have temporal coupling all along this request path while the entire thing is running. And that can give us some headaches under load because we bind resources along this request path. And when something goes south on a downstream system, this can have an impact on the upstream systems too, up to the end that it jeopardizes the stability of your entire applications. And this is one reason why we have mitigation patterns like circuit breaker in the first place. But also, it actually violates a little bit the promise that we got from such divide and conquer architectural styles like microservices, because one of the promises was that I can scale every system individually without any dependencies of surrounding systems. And that's not true if we use the synchronous request response model. Due to the fact that we bind resources all along that request path, we might also need to horizontally scale an upstream system just because the downstream system has some hiccups. So what can we do about it? We can maybe look into the asynchronous request response pattern with APIs. And the difference here is that the requester just shoots out the request to the downstream system, and then the connection is closed and the requester does something else. Eventually, the responder is done with working on the request and can send back the result. This comes, of course, as trade-offs, as we have learned previously. First thing is that the requester needs to keep state. I have sent out a request downstream, and I need to memorize what I have sent. Eventually, a response comes in, but how does the responder know where to send it? So that is a helper pattern that we call the return address, meta information that goes into the request and instructs the responder where to send the response. And the same applies to correlation ID, also meta information that you inject into the request, and the responder returns also to the requester, so it can then correlate, that's why it is called correlation ID, the incoming response with the request. So there is a trade-off, but with that we reduced runtime temporal coupling as much as we can do with APIs. And this brings us to the next insight, that, wrong button, friends don't let friends rely on synchronous integration. Unfortunately, the asynchronous request response pattern with APIs still leaves us with a degree of temporal coupling that may lead to trouble during runtime. Why is that so? Well, apparently, it's going to be difficult to send a request downstream to a system via an API if that downstream system is offline or in a struggle. So then we should probably look into messaging to help us here. In particular, point-to-point messaging with queues can help us here. Now, queues decouple producer and consumer in several ways. And the decisive pattern here, or the decisive effect for our problem that we identified that we cannot send an API request to a downstream system if it is offline, is that queues buffer messages. So they can flatten peak loads, or in any case, keep messages for the consumer in case it cannot catch up with the message load or it has some hiccups. Another very interesting effect in the characteristics of queues is that you can attach multiple consumers to it. We call it the competing consumer pattern, and that allows you to scale out horizontally on the consumer side depending on the message load that you have, and that is really helpful. The characteristics of queues are that every message is sent to one of those consumers, and therefore you can easily scale out on the consumer side. The most relevant AWS services that implement that point-to-point pattern, you probably know Amazon SQS or Simple Queue Service, which is a cloud-native and serverless message queuing system, or if you are bound to industry standard protocols like JMS or AMQP, often in migration scenarios, you can use Amazon MQ, which is a managed RabbitMQ or Apache Active MQ system. Okay, now let's see how the asynchronous request response pattern can be implemented with queues. So we have now logical channels that decouple in a temporal way, but also even in a location dependency way, because the requester doesn't know the location of the responder anymore. All right, and with that, we have the next insight that loose coupling is mostly better than lousy coupling. And I would say mostly is important to say here. As we learned in the beginning, there is no always in architecture decision. It depends, and it comes with trade-offs. So, but if you are under high scale and have these requirements, then loose coupling is definitely the way to go. And if you don't have any scale requirements and can live with this runtime dependencies, you wouldn't do the extra effort. But why don't we further illustrate all this with a real-world example from Amazon as an AWS customer?
Let's see how Amazon pays to their suppliers and service providers. In any financial transaction, there are two parties involved, payer and payee. Payer is the one who sends the money, payee is the one who receives the money. In today's example, Amazon businesses are the payers. They send money to different payees like digital authors, vendors, app developers, and much more. Today, our focus is on how Amazon businesses pays to vendors, vendor payment flow. So, who is vendor? Vendor are the one who supplies the goods to Amazon, which are available on the website for the customers to purchase. Once they supply the goods, they submit the invoice to retail invoicing system, which matches this invoice with the receipt from the Amazon inventory. Once the invoice and receipts are matched, these matched invoices sent to account payable system, which is responsible for accounting and enriching the invoices with additional information like tax, calculating the withholding tax, etc. Once the invoice is ready for the payment, based on the payment terms with the vendor, account payable system send the payment instruction to payment disbursement system. Then the payment disbursement system instructs Amazon banking partner to transfer the fund from Amazon banking account to the payee account, in this case vendor. We are going to see how the payment disbursement system is working. This is because it plays crucial role in sending timely and accurate payments to vendors. Here, the upstream services or Amazon businesses sends the payment instructions to disbursement service. This instruction has information like payee, meaning like who is the vendor, payer, which Amazon business, amount, and currency. Then we enrich this instruction with additional information which might be required by the banking partner. Once we enrich this information, we validate this information by calling the validation service, which in turn talk to lot of services like fraud detection service. Once we enrich, validate, then we send it to payment routing service, which sends to banking partner. Once we get the response from the banking partner, we send it back to upstream. As you can see, just to complete one disbursement request, multiple services has to work in reliable way always. So this architecture comes with some limitation and challenges like cascading failures. If any service in the chain become unresponsive, the entire transaction is going to be failed. Handle traffic spike. The traffic pattern of the upstream services are different, meaning some services send daily basis, monthly, sometimes real time also. So every service in the chain has to scale to handle this spiky traffic. Reduce throughput. This becomes particularly problematic when we integrate with external APIs whose throughput and latencies are totally different than your internal system. Eventual response expected. Here the upstream is not expecting the immediate response from the banking partner. The eventual response is totally acceptable. So after understanding the limitation and the system better, what we did, we tried to split the disbursement process into two steps. Step 1, we acknowledge the disbursement request. We do some basic validation. In step 2, we try to actually process the disbursement. Here we use AWS step function, which gives the flexibility to add or remove the steps based on the banking partner requirement. Also, in case of any failure, we can retry efficiently. We couple these two steps using queue, which provides some advantages like location. Here, producer and consumer don't need to aware of each other location. Availability. Producer can keep sending the messages without even worrying about whether consumer is available or not. Rate of processing. Producer and consumer can operate in different rate. Scaling. Producer and consumer can scale independently. But still, we haven't solved one important puzzle here, one piece in this puzzle, right? Meaning, whatever the response we got from the banking partner comes to the payment disbursement service. Now, the payment disbursement service has to send the response back to upstream. Let's say if we use queue, for every upstream, there has to be some integration done by the payment disbursement service. That means you need to do some code changes. Ideally, we want to completely decouple the payment disbursement service from the upstream. So what do?
Right, relying only on queues in this case would impose unnecessary coupling on your architecture. Particularly the location and the domain dimension are relevant here. So sending the same payload to multiple receivers, that can be done, of course. There's nothing wrong with having 3 queues in this example for 3 downstream systems, and you can send the same message to those. But it brings you domain coupling on the producer side, because in the request-response pattern that you typically then use, the sender of a message needs to make sure that it understands the domain of the consumer. But also you need to manage 3 locations in this case, right? So you duplicate the effort. And this is where messaging with topics, also known as publish, subscribe, or fan out, can help. Topics are different from queues in the sense that A, they don't buffer messages, and B, they send the message to all the registered subscribers. That's what the consumers are now called. That might have an implication on what we have already learned and loved with queues, because of the functionality of queues that they buffer messages for you. And also the scale out on the consumer side might be tricky now, because I cannot just add an additional subscriber to manage the scale or the load. The additional subscriber would also receive every message. But let's park that for a minute and rather look at the benefits of pub/sub messaging here. So now the publisher is totally decoupled from the subscribers. So it doesn't care about any domain models of the subscribers. It is rather that each of those subscribers needs to be responsible to understand the domain model of the publisher. So we reduced that load from the publisher. And also we minimized the location dependency. There's only one location it needs to manage. The most relevant AWS services implementing pub/sub messaging would be Amazon Simple Notification Service, or Amazon SNS, which is again cloud native and serverless, or also Amazon MQ as a managed RabbitMQ or Apache ActiveMQ. But how do we solve that problem that we just mentioned, that we don't have the message buffering functionality and the scale out anymore? There's a simple composer pattern that we can apply here, topic queue chaining. Instead of directly attaching the subscribers to the topic, we can put a queue in between, which is also a general recommendation that I would give to your architecture just to increase stability and reliability of your architecture. So we have the best of both worlds. We have the durable subscriber pattern, as we call it in this case, and we still have the competing consumer pattern for scale out. You may now ask yourself, what about buses? Everybody's talking about event-driven architecture, and typically a message bus is employed there. And you could have at least a 60 minutes discussion about when to use a bus, when to use a topic, when is it advantageous to do that or that. But to make it simple, the scope is typically different. For a message bus, it is an entire application or even cross applications. Also, the roles are a little bit different. In a PubSub scenario with topics, you typically have one party that is only a publisher and other parties that are only subscribers. And the scope is a part of a use case, as Balaji just shared in his example, and we will see an update of this also very soon. But an event bus is something, or a message bus, sometimes called event bus, is used in an event-driven architecture where you have the scope of an entire application or even cross applications. And it comes with additional functionality mostly, but maybe also some constraints, like you are constrained to a certain payload format. But it gives you also integration with commercial systems. The AWS service implementing the message bus pattern is Amazon Event Bridge, as you have probably heard. It's cloud native and serverless. But for the sake of the understanding of these concepts of fan out, PubSub, it doesn't matter if we discuss topics or buses today. It is all about this concept. We can now go back to our real world example and see how PubSub can be in action.
So, as I promised, we are going to solve the last piece in the puzzle, meaning how do we send the response back to the upstream. Here we used fan-out model. Here the subscribers, the upstream services, do not need to subscribe all the events from the topic. They can subscribe specific set of event using filtering policy in SNS. As you can see, decoupling introduced a lot of complexity, lot of moving parts. So we need a better mechanism to trace this request end to end, so we can debug any issue or monitor. So for that, we used correlation ID or end-to-end ID. Let's see. Now upstream sends the payload or request to the disbursement service. The disbursement service creates unique correlation ID or end-to-end ID sent back to the upstream. The same correlation ID is carried forward throughout the request across multiple components. Also, we send it back the same correlation to the upstream. So this helps us to stitch the request across multiple components. Then we started adding more and more features or use cases like remittance messaging service. The purpose of this module is to send an email or SMS on successful response. So this module also listens to the same topic, but only filter the successful response. Again, they use filtering policy. Bank account status tracker. There might be a situation where the payment is failed because of incorrect bank account. We don't want payees to wait for the next payment cycle. Rather, we want to notify the payee immediately, then we can validate it so the next payment cycle can go through successfully. So the responsibility of the module is to listen to all the events which are failed due to incorrect bank account. Another module is bank response processor. This is similar to like coupling where you have a spectrum, right? Similarly, the bank responses are not going to be success and failure. We'll have a different response code. We need to understand what action we have to perform based on the response code. So this module listens to all non-successful events and figure out what action that system has to take. I can keep talking about this coupling for next 1 hour, but we have more concepts to cover.
Right, and the next chapter is control flow and flow control. There's no pun intended here. Those are two important aspects that we should have a look into. Control flow, let's approach it from this angle versus data flow. In most architecture diagrams, also in the ones that we have seen so far, we discuss data flow, but control flow can actually be different. It can even point into the opposite direction. When you look at the pull model, then the receiver actually initiates the conversation. And that becomes also very clear when we look at this for queues. So between sender and queue, it's quite simple. It is a push model. The sender pushes messages into the queue. But between queue and receiver, it's the other way around. And it has to be because we want to enable the queues to buffer messages. And we cannot do that if the queue just pushes out messages to any consumer. So the consumers need to initiate this conversation. So we can see that data and control flow can point into the opposite directions, which brings us to another insight, that control flow influences dynamic system behavior, such as latency, scaling, batching, and timeouts. You can easily imagine, for instance, looking at queues, that it adds a little bit of latency because of the pull model from the receiver side, but that is yet another little trade-off that you need to pay when you get the benefits of queues. And I mentioned already that queues can nicely flatten peak loads for you, and that's really very cool if you are under high load. You only need to take into account one thing. If you have constantly fast producers and slow consumers, your queue size fills up, and that may lead to problems. There are basically two toggles that you can apply here. The first one is time to live, and the second one is back pressure, also known as producer flow control. So you need to send a signal to the producers if you cannot catch up with your messages, hey, slow down a little bit. That could also be rate limiting applied in a API gateway that is in front of your queue. Now, we can also see this in action when we look at serverless Presso. You will find this also in the expo. It is a serverless application that manages coffee orders and baristas who do the coffee. And also here we have back pressure, because the bottleneck in such a scenario are the baristas. They can obviously only do so many coffees at a time unit. And if they are all busy, then your next order maybe needs to wait. Obviously, back pressure is something that consumers hate, particularly when they are human, but if you are limited in resources, that's the way you go. You see it in the step functions workflow that manages serverless Presso. There's an explicit choice state capacity available, and if not, they don't accept the next order. Which brings us to the next insight: queues decouple control flow, but require flow control. Let's move on with the next chapter, message order and delivery semantics. And here we look first into FIFO channels. And we start with a provocative statement. Message order is frequently requested, from time to time, even with good reason. Of course, there are situations where you must have this, but our mental laziness makes us want this all the time and rather ignore the trade-offs. In principle, it is quite simple. We have FIFO queues, and with a single consumer pattern, it is not very complicated. We just want to make sure that messages are sent to the consumers in the same order. It becomes hairy when we look at concurrent consumers. So for that, we actually need, and we will also see very soon why, we need a helper pattern which is called message groups. And that is a discriminator attribute that we put into our messages. The way how Amazon SQS FIFO queues implemented is message group IDs, which is as I said, a discriminator attribute that goes into every message. So if we partition all our messages into groups, as we see here, we have 3 groups, the blue one, the green one, the orange one. Let's run through how Amazon SQS FIFO manages the consumption or the delivery of those messages. So we deliver the messages in the right order, and you can see already we have no control over the consumers here. So the processing of one message might take longer than of the other, and we scramble the overall order here because B is done sooner than A. We would actually now expect that message C is delivered, but it isn't. It is message D. Why is that so? So the way that it works is that as long as one message of a certain message group is in flight, that means sent to a consumer, not yet acknowledged, so deleted from the queue, SQS will not send another message of the same message group to a consumer. And this is why we continue with D. Eventually, A is also done, and we can follow up with C. So as we can see, in the end, we have scrambled the overall order of our messages, but we have kept the order within our message groups. And that is the decisive insight here. Order of messages in distributed systems is relative to a defined scope. And now if you say, I need total message order from the beginning of all time to the end of all time, there's only one way to physically do this. You need to degenerate into sequential processing. If you have concurrency, this will not work. But even if you have such cool features like Amazon SQS FIFO queues, there might be business requirements that still need you to apply additional engineering.
Let's go back to our vendor payment flow. Now our focus is on the tax system. Specifically, we are going to discuss how we calculate withholding tax. Invoices can be updated for various reasons. It could be as simple as updating some line item description. Sometimes these changes may influence the withholding tax value. It's very important that we process this change in the same order it occurred. Sometimes when we process this change, it may take days, weeks, or even months. But we cannot hold back the acknowledgement back to the messaging system for that long period of time. So we built custom solution on the consumer end using DynamoDB. This slide has a lot of moving elements. Let me first try to explain before we go into example. First, there are 4 changes. Change A and C belongs to invoice 1, has the same message group ID. Change B belong to invoice 2, has a different message group ID. Change D belong to invoice 3, has a different message group ID. And the table workflow execution table. The purpose of this table is to store the active change that is being currently processed by the system. In this example, let's say if the system is processing the change A for the invoice, then you will see the record in this table. Once this change is successfully processed, that means once we successfully calculated the withholding tax, then we remove this record from this table. Event audit table. The purpose of this table is to store all the changes happened in all the invoices. Here the partition key is invoice ID and the sort key is the change ID. Status. There are 3 possible status the change can happen. One is active. That means the system is actively processing this change. Second, completed. Once we calculate the withholding tax, the status will be flipped from active to completed. And third one is the pending. If there is an active change for a given invoice, if the system is processing, any other change will be added into this table as a pending status. The last one, which is interesting, is an LSI. We use the same partition key, which is because of LSI. And in this LSI, we store these changes in the chronological order. Just to compare, consider a FIFO queue. In the given message group ID, all the messages are maintained in the same order it arrived. Similarly, in a given partition key, all the changes are stored in the chronological order. Going back to the example, right? In the FIFO queue, once we consume the message and successfully process, then this message is no longer visible to other consumer. Similarly here, what we are trying to do is, once we successfully process this change, we don't want this change no longer visible in LSI. How do we do? Simply update the value to null. Once we update the value to null, then this change is no longer visible in this LSI. Let's see it in an example. So here change A, B, D are visible to consumer. Change C is not visible because belong to same message group ID. Until change A is successfully processed and acknowledged back to messaging system, change C will not be visible. Now let's say the consumer is processing change A. Since there is no active change for a given invoice 1, so this change becomes an active change. We insert the record into workflow execution table, and in the audit table, we add it as an active. Once we insert into an audit table as an active, we have a DynamoDB streams, the Lambda, we have a custom logic, which will invoke the workflow, which actually does the withholding tax calculation. Now if you notice, change C is visible. This is because once the change A consumer insert the record into the table, it acknowledged back to the messaging system saying that I have completed my change. So the change C is visible. But actual withholding tax calculation is happening through the workflow. Now let's say we process the change B. This is similar to change A. This is a new active change. So it insert into workflow execution table with invoice 2, change B, and event audit table status as active. Once it becomes active, the DynamoDB stream kickstarts the workflow to calculate the withholding tax. Interesting. Now change C comes. It looks into the workflow execution table. There is an active change, which is change A for the invoice 1. So this change C cannot be processed. So what we do, we insert into event audit table in a pending status. If you noticed, all this write operation done in a transactional way just to avoid any race condition. Once this record is inserted into pending status, this will not kickstart the workflow because the DynamoDB stream Lambda, what we wrote, it will kickstart the workflow only if the status is active, not for the pending. Now let's say change B, the workflow completed. We completed calculating the withholding tax. So the now workflow comes back and it does two important things. One is it removes the record from the execution table. This is because no longer the change B is active. It is completed. So we don't want that record to be in the workflow execution table. Then we have to remove this change from the LSI. Like we discussed before, if we want to remove this change from the LSI, we update it to null and flip the status to completed. And at the end, from the consumer perspective, the change B is completed. Now let's say we process change D. Same story. The new change for invoice 3 added into the execution table, event audit table as an active. Then DynamoDB kickstarts, the workflow starts for the withholding tax calculation. Once it is completed, it comes back, delete the record in the execution table, and remove this change from the LSI, flip the status to completed. At the end, change D is completed. Now the fun part, the change A is completed after a long period of time. Now the workflow has to figure out what is the next active change in this queue. So what it does, it goes and looks into this LSI. It figures out the next change in the queue is change C. So then workflow comes and updates the execution table from change A to change C. And since the change A is completed, it updates the status to completed and remove from the LSI and flip the status of change C from pending to active. Once it becomes active, and also change A completed, by the way, from the consumer perspective. Once the change becomes active for change C, Then it triggers the workflow which calculates the withholding tax, and the same thing. Once the change C is completed, we remove this record from the execution table, we remove this record from the audit table, and at the end, the change C is completed. So as you can see, we are able to maintain the order on the consumer side, even though the change A took long time, even it could be in months also, still we are able to maintain the order. Okay, so let's move on to the next chapter.
Right. We have a few other aspects in message order and delivery semantics. The first one is deduplication, and we can again start it with a provocative statement. Message deduplication is frequently requested from time to time, even with good reason. But also here again, we need to be aware of the scope. What can we do on the producer and on the consumer side, or how can we influence producer and consumer with certain patterns here? If we look at Amazon SQS 5.0 again, for deduplication of incoming message, there is a 5-minute interval where it checks for a deduplication. And you can easily imagine that it is virtually impossible to do something like this from the beginning of all time to the end of all time. Similarly, on message consumption, there are concepts like the message visibility timeout that also needs to be finite, otherwise you will certainly run into starvation problems. So also here, the insight is that deduplication of messages in distributed systems is relative to a defined scope. And then we also have how often delivery. There's always something that architects and developers discuss, like we need exactly once delivery, processing, whatever. Let's call it exactly once dingus. And even if you use all the deduplication option for producers and consumers, you always have the challenge on your own code that you can run into exceptions while you process something. And then the big question is, what do you want to have? Do you really not want to see that message again? Do you want to manage everything manually, to roll back, to reprocess something or so? And typically the root cause for all this is that architects and developers have a little bit of a fear of idempotent processing. But again, the ugly truth is you can hardly avoid failure situations. In fact, you can't avoid failure situations. And therefore, idempotent processing is something that I would recommend to everyone. And it is not necessarily as difficult as you might think. And there are also tools that even support you. For instance, if you use Lambda, I can recommend AWS Power Tools for Lambda that supports you also with idempotent processing. Speaking of failure and trouble handling is certainly also very important in distributed systems. And some words of wisdom from our CTO: everything fails all the time. And there can be some scary patterns like poison pills and dead letter channels that might help you. So you need to embrace failure, because only then you can manage failure. What are dead letter queues in the first place? So let's look at this example here. We have a few messages that go into a queue and are consumed, and then we have repeatedly an exception when we process message C. We don't want to have that going on forever. That's why we can then employ the pattern of a dead letter queue and reroute this message there, take it out of production, and we can inspect it without open heart surgery in production. Why don't we look at how this is implemented in the real world example?
So let's go back to the example. How many of you think the solution will work even with the error condition? So no one has confidence? Okay, thank you. So let's see. Let's try to play the same example with the error condition. Now let's say we process this change A. For some reason, some exception happens. We keep retrying at the predefined number of times. After that, we gave up. Then this change or message goes to DL queue. Now we pick the change C. Going back to the same thing, there is no active change being currently processed for the invoice 1, so we insert into execution table as well as event audit table with the status as active. Once it becomes active, we trigger the DynamoDB streams lambda, which kickstarts the workflow to calculate the withholding tax. And at the end of the workflow, we delete this record, we delete this change from the LSI, flip the status to completed. At the end, change C is completed. Now, when we try to redrive these failed messages, now the change C is again picked up by the consumer. Let's say this time there is no exception. Now you see there is no active change for the invoice 1. So system considered this is the active change. It's tried to insert this record into execution table, also in the event audit table as an active. So now it is violating our requirement. We don't want to process the change A if we have already processed the change C, which is the latest one. So what we did, we tried to add a couple of columns in the execution table and one more change. So here we added the status, whichever the status column in the event audit table, we try to do it, and the timestamp. The timestamp here is not the timestamp when the change or message came to FIFO queue or the timestamp when this processor processing it. It is the timestamp actually the change happened at the invoice. So the source system tells this change happened at this time. This is part of your information in the message. So we store the timestamp. Let's see with the change. Let's say the same exception happened, we retry predefined number of times, we gave up, goes to DLQ. Now we process the change C, insert into the workflow execution table and audit table status as active, the same thing. The streams kickstart the workflow, we calculate the withholding tax. Once it is completed, update the status in both the table as completed and also remove from the LSI. At the end, change C is completed from the consumer. Now, when we redrive this failed message, in this case change C, now the consumer look into the execution table, it sees there is a change which recently completed, that's fine, but it compares the timestamp. The timestamp of change A is T1. So now the consumer knows there is an already latest change has been already processed by the system. So in our use case, we want to skip the change. But still for audit purpose, we want to insert this change in the audit table as a skipped. Once it is added as a skip, it is no longer going to kickstart the workflow. So that brings end to this example. We have one more section to cover.
Let's look at archive and replay. And let's now also employ Amazon Event Bridge. So let's assume we have a message bus here in the middle. We have some producers and consumers. As I said before, they can be both prosumers, but in our example, it is from a certain use case that we have a producer of messages on the left and consumers on the right. And the rules that those consumers apply are that the first one receives the purple messages and the second one the blue messages. So all good. Messages go through the bus, are delivered to the consumers, are processed there. You can also, for resilience, add a queue in between, just for illustration. But eventually, all the messages are gone from the systems. You have your processing code. 2 weeks later, maybe you identify that there is a bug in the code. And you would actually reprocess it, but those messages are gone already. What could we do here? So now we could maybe make use of the archive and replay pattern, which is supported from Amazon Event Bridge, and by the way, also with SNS FIFO topics. So you keep those messages in an archive, and at a later time, when you see you need to reprocess those messages, you can just fire them through the bus to your consumers. I have changed the colors a little bit because one thing you need to be aware of is that, for instance, the message ID changes here. So with that, you can actually solve that problem. But hey, that gives even more ambiguity because until that was supported by certain messaging systems, message replay was a unique selling point of streaming. So that makes it yet again a little bit more difficult to decide when to use what. But for sure, the consumption model stays different. So that's something that is still a distinction between both approaches. And again, since you want to reprocess messages, of course, you should have idempotent consumers. And since in this case, EventBridge really fires those messages out as fast as it can, make sure that your downstream systems actually can handle the noise. One last thing that becomes relevant if you have a multi-tenant architecture in your distributed system, if you are a SaaS provider, is the problem of noisy neighbors. But it is not limited to actually multi-tenant architectures. It is a problem that can always come up when you deal with shared resources. But since we are talking about messaging all the time here, let's have a look at, with the example of a queue, what a noisy neighbor actually is. Let's assume we have 3 different tenants here. Messages on behalf of those tenants are sent into a queue, and the typical architecture that companies start with is one multi-tenant queue for all tenants. But what happens if one tenant starts creating a large backlog of messages? That might come through input, new messages created at high scale. It might also be due to some exception on the message processing side, so that those messages get back into the queue at high scale. In this example, we have tenant 1 here who has a dominance in this queue now and has built a large backlog. So if this becomes a problem, there are a number of mitigation patterns, and we could talk for hours about all these. And that's why I only mention the typical mitigation patterns here. You could actually always apply what we have learned before, the back pressure and load shedding with TTL, time to live. But then for all the other mitigation patterns, there is some additional engineering that is required here. For instance, dedicated single-tenant queues per tenant, and hybrid architecture, cell sharding. It becomes more and more of an effort of engineering that you need to apply if this becomes relevant for you. And again, you would, of course, only do this if you have those pain points. If you don't have those pain points, you would certainly not do. All these mitigation techniques come with trade-offs, of course. They give a benefit, and they require you with additional engineering effort, which brings us, again, back to the very first insight that we had. No architecture decision you take comes without trade-offs. And to conclude, and as a takeaway, let's have a quick look again at the distributed system fundamentals that we discussed today. We looked into those 4 pillars: coupling and its dimensions, control flow and flow control, message order and delivery semantics, and failure and trouble handling. All right, so we can now conclude this talk with the next steps.
So if you want to learn more, we have assembled few resources that you can download from this resource page, s12d.com/API306-24, or you can scan this QR code. I will leave that up for a few moments for you to scan. We also recommend to check out these other sessions related to our content. First one has already completed. It's a breakout session. You may watch the recording.
Right, and then some advertising. If you want to continue your serverless learning, you can go to this site, and there are free courses. You can earn badges there. And as I mentioned already, I can only recommend to you AWS Power Tools for Lambda, which I will show you also once you took those pictures. You can download it from there. And other than that, thanks for being here with us today. Was a pleasure. And if you want to reach out, please find us on LinkedIn, and we will also be around for questions now. Thank you.